All right. Hello, everyone. Thank you for being here, Eric. Eric is a postdoc at UT Austin. He's focused on program semantics, verification, and synthesis for open systems. But I have known him quite a bit longer than that. In fact, we had the same advisor at Cornell, where he earned his PhD. And there he developed tools for verifying and specifying P4-based network programs. His research spans networking, databases, OS, and AI systems, with an emphasis on practical and scalable formal methods, which I think is the key point that he'll be telling us about today. Take it away, Eric. I'm excited.
Yeah, thanks, Jonathan. In fact, beyond just having the same advisor, we sat across from each other for many years at Cornell. So it's great to be, sharing what I've been working on since with you and the rest of the P4 folks. So today I want to talk about how we can augment our understanding of data plane programming with some formal logic techniques. The title of my talk is When P4 Isn't Enough, which is slightly provocative. But mostly what we're going to focus on is how we can write specifications and think very carefully about what those specifications should be for the interface between the control plane and the data plane. And we'll explore some cool things you can do once you have those specifications in hand. So let's start with a problem that's simple to state but quickly gets out of hand. Imagine you're building a software-defined network. You've got routing, load balancing, access control, the usual suspects that have been written against a control platform, something like ONOS. And then you've got some clean P4 programs that you've written for each of your switches. Well, clean might be an overstatement, but you've got P4 programs for each of your switches. So far, so good. But the infrastructure team buys some new hardware, and a new P4 program is written to accommodate the new hardware. Or if you're like Jonathan at Google, you've bought some fixed function device and you've written a P4 program to specify the behavior of that fixed function device. And writing this program or the specification is one challenge, but today we're going to focus on how the control platform can and should talk to all of these different programs consistently. And that's where things are going to start to get pretty messy. So let's dig a little bit deeper. These control applications are written against some high-level routing abstraction, something like OpenFlow or SAI, the switch abstraction interface, or ONOS's fabric.p4. But the reality is far from uniform. This nice abstraction has to be compiled to the unique table structure of each switch program. And each switch program is different. There's different matching semantics, different match kinds, actions, pipeline orders, which means each switch and each P4 program gets its own driver that respects the semantics exactly. And so adding a new switch means writing a new driver that can accurately implement the desired forwarding behavior for that new switch, taking into account its idiosyncratic variation. And managing these unique features across a fleet of heterogeneous switches is kind of a mess. You end up relying on a lot of very careful engineering and English specified, or worse, undocumented assumptions. And when those assumptions break, so does your network. So the question is, if each switch is quirky, can we get a handle on that quirkiness before we start seeing bugs in production? In other words, what can I know statically? What can I know in advance before I even compile my P4 programs? The first thing we're going to look at is safety, by which I just mean under what conditions is the switch safe to use? What assumptions has the programmer of the new P4 program made? And what, if any, latent bugs exist in the program that I need to work around? And if we can fix them, we can fix them, but sometimes we can't. The second thing we're going to talk about is compatibility, which is even if a switch is safe to use or has some conditions under which it's safe to use on its own, is it compatible with the abstractions that my control plane is already using? Will it faithfully implement routing, access control, load balancing, etc., in the same way as the rest of my data plane? Or are there subtle differences in match semantics, say, that break my network logic in ways that only show up at runtime? And as far as I know, these are questions that there's not really existing tooling to answer. And so in this talk, we're going to talk about some work that I presented at OOPSLA about safety, and some ongoing work where we reason about compatibility. Okay, let's start with safety. At first, it sounds simple. Is the switch safe to use? But in practice, the switch safety relies on complicated invariants on the table entries that are installed. A prime example is undefined header reads. In P4, if a header is invalid and you try to access a header field that hasn't been properly extracted or set to valid, then the value that you get out can be undefined, which means it can be anything. It can be the value from the previous packet. It can be some random bits. It could be all zero, something like this. Which means that if it appears as a key in a table, that the actual value of the actual action and the entry that gets matched in that table and the action that gets executed can be unpredictable. So in this table, which has keys ether type, IPv4 destination, and IPv6 destination, and it selects one of three actions, route, drop, or no action. Well, the validity of IPv4 and IPv6 is mutually exclusive. That is, if one is valid, the other definitely isn't. And this is sort of prime real estate for undefined behavior. And okay, there are architectures where they can both be valid, but like let's stay simple. And right, we can witness undefined behavior if we're not careful here. Okay, so our solution is to augment the table with control specifications, which constrain the tables that are legal to install while maintaining our sort of predictable behavior. Here, we can ensure that whenever the ether type indicates that the packet should be IPv6, then the IPv4 destination is wildcarded with some kind of don't care value. And we have the symmetric condition with the ether type when the ether type indicates that the packet is IPv6. And luckily, this is a perfectly feasible condition for the control plane. IPv4 packets should not be forwarded based on the IPv6 address and vice versa, unless something is wrong, in which case we want to know about it. So how do we use control specs to see that we have gone wrong? We can look at an example configuration of this table. This first rule, which says that the packet is IPv4, it wildcards the IPv6 destination. This is great. Matches on the IPv4 because the packet is IPv4. The second rule does the reverse. It says that the packet is IPv6 and it matches on the IPv6 address. The third rule, something has gone wrong. The type indicates that the packet is IPv4, but the IPv4 destination is the one that's wildcarded, and we try and match on this IPv6 destination oddball, and this doesn't make any sense. This entry violates the specification. Assuming some simple pipeline, we could end up with undefined behavior here. Okay, so now with this story, all we need to do is write down a control plane specification and check that the switch tables and its entries conform to it. And when it doesn't, we can report bugs that we found. But there's a deeper problem, which is how do you know that the spec itself is any good? How do we know that actually satisfying the specification prevents all bugs that may appear in this new P4 program? And so we're going to talk about how we can verify the safety of these specs, and then move towards inference, where rather than putting this manual effort of writing down specifications, which generally is something only done by people who have formal methods background or programming languages background, we can infer the specifications and produce sort of formal checkable control specs. Okay, so for one, if we're given a control spec and a P4 program, it's pretty straightforward to check whether a program satisfies that spec. A bunch of folks at SIGCOMM 18 applied some classic techniques invented by Dijkstra and some cool optimizations by Flanagan and Sachs to build a verifier called P4V that takes in a control specification and a P4 program and says, hey, there are no bugs, or it says, look, I found a bug. And in this view, well, we have to write these specs by hand, which in general can be pretty painful. And as I said, sometimes requires special training. So the big question is, how do we go from a P4 program to a specification in a way that ensures safety, ensures that there are no bugs so long as you satisfy the specification? How do we compute this control spec? Well, that's what Capiche does, which is this tool I mentioned before that we presented at OOPSLA 24, which computes a control specification from a formal model of the P4 program. And not just any specification, but a specification that is formally guaranteed to be the most permissive. In logic parlance, this is the weakest specification. Now, all the messy assumptions that are baked into the execution model of the P4 program have been lifted into a formal specification on the control interface that is guaranteed to ensure safety. So let's get a sense for how the algorithm works. Basically, we start from a formal model of a P4 program and some trivial starting specification, true, and we use a homegrown verification procedure, just like P4V, to check whether P4 is bug-free under the specification fee. If that's the case, then we return that specification because we're done. Our spec is sufficient. Otherwise, our P4V-like verifier returns a bug from which we extract a packet that witnesses the bug, that when executed on the switch will trigger the bug. We then use something called an error localization strategy, where we analyze the P4 program with the packet to determine something called a program slice, which is the set of subcomponents of the P4 program that cause this particular bug. And then we do root cause analysis on that to produce a specification C that describes the cause of the error. And then we prevent it by conjoining its negation to the previous specification. The cool thing about this algorithm is that it's formally guaranteed to terminate, and, as I said, guaranteed to produce the most permissive specification, which means that the fewest constraints are placed on the control plane. Okay. Oh, right. You can join the spec. Okay, so Capiche works well. We surveyed a bunch of open source P4 programs. Please don't try and read this. You can look at the details in our paper. I just want to sort of show you that we did do an evaluation. The cool thing I want to focus on is that we found a bunch of bugs because the specs looked funny. So we looked at the specifications, read them, and found a bunch of sort of canaries in the mine, if you will. We call these code smells, specification smells, which are related to the idea of code smells, that indicated that there were deeper structural issues with the P4 program. So the first one is called obligatory wildcard. And the idea here is that if you read the specification and you see that in some table, a key is always required to be matched with wildcard, that's a problem. Why is that key in the table if you always have to wildcard it? Something's wrong. Similarly, there's prohibited action, which is the same idea but applied to actions. Why is an action in a table if you can never execute it? And finally, this is a little bit funny, but if Capiche took a long time to complete, that was typically indicative of a larger problem. For the few examples that we had that took a long time, we were able to analyze subprograms of Capiche to identify the issue. Once we fixed those, Capiche ran in seconds. So in the context of incorporating a new switch into an existing software-defined network, observing these canaries is likely indicative of a bug, which either should require the data plane program to iterate on their program design, or in the case of specifications of a fixed function switch, might indicate that that switch is incompatible with the network. Okay. So with Capiche, we're able to analyze P4 programs and compute specifications that, when satisfied, ensure there are no bugs in the program, that they're safe. These specs are also the most permissive safe specifications, meaning that they minimally restrict the control plane's behaviors. And I didn't talk too much about this, but generally, the specs are efficient to compute in practice. And in my anecdotal experience, generally efficient enough to be used in the loop of writing switch programs. And when they're not, well, that itself, as I said before, is indicative of an issue in the switch design. We've also proven in the paper that in a theoretical sense, they're efficient to check. You can see the details there. Okay, so going back, safety alone, even though we get some hints from reading our specifications about whether a switch might be compatible, it's not enough to ensure that a program can safely be incorporated in the network. We need to check a more nuanced property called compatibility. Every time we get a new P4 program, we have to ask, is this program compatible with my existing network functions? And one big challenge here is that this high-level routing abstraction from which we need to write our drivers is often not formally specified. One notable exception is Onos's fabric.p4, where they have this specification of their flow objective interface. But generally, this is not the way the world works. What we can assume is that we have formal models, that is, P4 programs of the existing switches in the network, and for the new one that we would like to add. And we can check compatibility by checking whether the new P4 program realizes or can realize all of the behaviors permitted by the control plane specification of the old P4 program. Our nascent project Spectacle is a framework to formally verify whether two network programs, are truly compatible by answering the question, can the new program, modulo its specification, realize all required specifications, that is, required behaviors, that is, those behaviors denoted by the old program and its control specification. Okay, example time. Let's say that the old program bundles all of the routing logic into one table. It computes the output port, it does the Ethernet header rewriting, it decrements TTL, all of that in one table. The new program splits that logic across two tables, next hop and rewrite, where the next hop table just computes the outgoing port, and the rewrite table does all of the header rewriting required. So what does it mean for these programs to be compatible with each other? Well, at first blush, these programs are inequivalent. They rely on different sets of tables that invoke different actions. But we're in search of a more nuanced notion of compatibility, which says that the new P4 program should represent all of the behaviors in the old P4 program, which clearly is the case here. So how do we think about doing this? To get an answer to this question, we need some more structure. A naive definition of compatibility is to say, let's install any set of match action tables subject to their safety constraints and check equivalence of the resulting packet processing behavior. But this doesn't work. In this example, it's very easy to configure next hop and route to map different IP addresses to different ports, and then route and rewrite to do the same thing with the rewrites. But this approach is fairly antagonistic. In some sort of moral sense, to be fair to the new program, we should really only consider those tables that try to implement the same functions, whatever that means. Formally, we model this by requiring a pair of functions between the spaces of tables. One that maps every table of the route, every route table, to a pair of next hop and rewrite table. And we need a function that maps in the opposite direction. Every pair of tables, next hop and rewrite, into a routing table. Let's see what I mean by example. Okay, so the route table, as I said, matches the IPv4 destination and then routes traffic out of port with a destination MAC address and a port. The MAC address here is just 4 bytes. In the new program, the next hop table computes the egress port number, and the rewrite table updates the MAC address. We can map from route to next hop by for every rule, just copying the IP destination address into the IP destination address. And for every route rule, we insert a next rule and we copy the port address. Great. Then for rewrite, we do something similar. The new destination gets plugged in with the same IPv4. The new IPv4 destination gets plugged in with the same MAC address. And of course, across the board, drop remains drop. And under this relationship, as we can see by this example, the programs are equivalent, and we could prove this. In the other direction, it's a bit more complicated, but the basic idea is that we join rules that have the same IPv4 destination, and if the actions are next and right, then we join them together into a route action on the port and the destination address, and then if anything is dropped, then we drop. And again, under this relationship, these programs are equivalent. But we can't just take arbitrary forwards and backwards functions because things will get even more complicated. So we're going to simplify our lives by providing some well-formedness constraints. Namely, that these transformation functions behave like inverses. Running one transformation forward and then running its reverse produces the state you started with. And the same thing, the same thing is true if you run backwards and then forwards. And we want this kind of property to make reasoning about consistency easier. In this context, we don't have to go down the complex distributed systems angle of achieving something like eventual consistency. These rules ensure consistency after one update to either side. If you update the tables on the left, run forward, you've achieved consistency. You don't need to run backwards because it won't give you any more information. In practice, we use a slightly more general notion of inverses augmented with state. And the goal here is to ensure immediate consistency, that after a single update, either forwards or backwards, you don't need to run any more. And the way that we model this is we use some PL magic, where we model the state as an extra parameter to each function, and as a secondary output to each function, here x, y, and z. So we say that if we run backwards, so forward takes in s and x and produces t and y. T and s are still the relative sets of match action tables, and x and y are whatever hidden state that the program needs to maintain. Then backward, when run on that table and the new state, produces the original set of tables and does not make any changes to the state. So z and y are equivalent. And we make the same sort of constraint in the other direction. These near inverses or stateful inverses are formalized in this classic paper from Poppel 2011 as symmetric lenses, where forward and backward are called put L and put R, but we've called them forward and backward here. And in fact, I know that, Jonathan, you've been using something like this to synchronize switch variation over time. So thanks for being here. So let's see now how we can prove something about these lenses. At this point, there's a lot to verify. Aside from verifying the lens laws that I showed on the last slide, we need to verify a couple of complex program equivalence conditions. First, we need to say that if a set of tables that satisfies the old control spec and produces a new set of tables T for the new P4 program that also satisfies the control spec for the new P4 program, then the two programs are equivalent on all packets. Okay, and then we also need to show something very similar in the reverse direction. And the challenge here is there's a lot of repeated work. Forwards and backwards comprise a lens, so it's very likely that they're going to be structured very similarly from a logical perspective. And then whatever traversal that's necessary to reason about old and new also has to be done twice here, and we're sort of repeating unnecessary work in doing these proofs. So we're going to jump into some PL theory again, and we're going to go back to a really old idea called constraint maintainers from 98, which we're adapting for lenses into a concept called lens contracts. And the idea is that we can verify that these pair of functions, forward, backwards, satisfies a lens contract theta. And if that's the case, then we can use this lens contract in our proof of correctness and only reason about old and new together once. Okay, so let's see what I mean. Formally, theta is a relation on sets of tables T and S for the old program and the new program. And the idea is that if you run forward on a set of tables and produce a new set of tables T, then that pair of sets of tables should satisfy the lens contract. And the same is true for backwards. So if you have this assumption, this contract, then you can write one proof, or do some verification about a single pair of programs, the old and the new programs, because you only have to reason about those sets of table configurations that satisfy the lens contract. Okay, so how do we actually check this verification? Here's our verification goal, and we're going to use a construction called the product construction, where we take the two P4 programs and we produce a single output P4 program. The way that we do this is we rename all of the identifiers in the two programs, and by all of the identifiers, I mean all of them: tables, metadata, standard metadata, externs, etc., everything. And the point here is that we get two new programs that are now guaranteed to use disjoint sets of identifiers. so that when we compose them, they don't interact with each other. There's no interference of state, there's no interference of packets. They're completely disjoint, but expressed in the same single program. Then we can produce this new, okay, it's not actually a P4 program anymore because that doesn't really make sense, but okay, we've modeled these things in some theoretical way that allows us to do this. And the key trick here is that we can encode disequality as a bug by saying, assume that these sort of disjoint sets of identifiers corresponding to the old program and the new program are equivalent. And then it must be the case that at the end of running both programs, the outputs are equivalent. And so if that's violated, that counts as a bug. And so now we can go back to our verification on single programs because we have a single program and we have an encoding of a bug. And so if we have these proofs that forward and backward satisfy the lens contract, then we can go back to our sort of program verifier and verify that this specification is sufficient to prove that this product program is bug-free. And remember that bug-free means that there's no disequality. So if there's no disequality, then the two programs are compatible with respect to this lens contract. Now, if we can't prove this, we don't get to say that they're incompatible. We can just say that we don't know. But what we do know is that this lens contract is insufficient. So, okay, we need to go back to the drawing board and write a new lens or write a different lens contract. Okay, and at the moment, this fully automated verification vision is a bit hypothetical for some technical reasons, but we have built a manual verifier using a program logic and some cool combinators in an embedded DSL. And so here's a very simple proof. Again, I'm not going to go through the details, but this on the right, this is sort of the proof if we had done it manually. And on the left is sort of, we've done some proof automation and stuff like this so that we can write the proofs basically as a product program itself. Okay, and the goal, which shouldn't be too big of a reach, big of a lift after building this manual verifier, is fully automated verification and potentially even the synthesis of these functions, of these lenses and the lens contracts. But that's still ongoing. Okay, so we've talked about control specifications, and we've seen how they work, how they can augment our use of P4 programs. With Capiche, we can infer and verify control plane specifications in a way to guarantee the safety, the bug freedom of our switches at runtime. And with Spectacle, we can prove compatibility between old and new programs, ensuring that the network keeps behaving as intended as it evolves. Okay, that's what I got. I'll take your questions now.
Very nice, very nice.
Great.
Excellent talk.
Thank you.
Thank you, Eric. So let me maybe start with some quick clarifying questions. I guess one thing I would, while I have you going back a few slides to the introduction of this inference algorithm for predicates, can I ask you quickly, I guess, as an avid user of P4 constraints, which maybe some people in the audience might know and some people may not, how does this relate to control specifications, right? So I guess for the people who don't, P4 constraints, right, is this kind of small domain-specific language that you can attach kind of to a table to give certain constraints on what are allowed keys and perhaps key combinations and relations between keys.
Yeah, so P4 constraints are contained within what we count as P4 as control specs. So they're sort of a restricted small set of P4 constraints, and I don't think of control specs. And I think that we wouldn't be able to achieve our theoretical results with control specifications. So, sorry, with P4 constraints. And the reason is that sometimes you need to reason about many tables at once. And P4 constraints are typically affixed to a single table at a time. And I think you have some, maybe we've talked about this in the past, I think you have some like foreign key style constraints that let you say something limited about pairs of tables. But really in our experience, we found that our uh, that safety properties require reasoning about 3, 4, 5, 10 tables sometimes. Um, so yeah, so yes, you
Cool.
could feasibly use this algorithm or something like it to infer P4 constraints, um,
Right.
but you wouldn't be able to
Well,
get the theoretical guarantees of permission, basically.
right. And indeed, presumably you could use this sort of verifier, I guess, in kind of the opposite direction.
Yes,
Since control specs, right, that could
yes,
be used instead of P4 constraints, for example, if you wanted to.
yes, exactly. You could use some kind of P4 verifier to check the consistency of the safety of the P4 constraints that you've written down, for sure.
Right. So now, I guess here I'm trying to figure out from this picture. This is exactly the one I meant. Thank you. I'm trying to figure out a little bit about what your safety property is here. So it
Good
seems to
question.
be like, what does it mean to be a bug here? Normally,
This
I
is
guess I expect this sort of arrow and check mark to say, oh, it doesn't satisfy this, so therefore
that's right.
there's some sort of bug, and I have a counterexample. But if you start with true, I would naively expect many P4 programs to satisfy that. So
Yeah,
I guess,
no, no, that's right. So we're sort of going in the other way. There's a hidden third specification that I've
uh,
sort of elided, um,
hmm,
which is what I mean when I say there's a bug, right?
mhm,
So the way that our tool works is that we have instrumentations that go through and instrument the program with assert statements that characterize um, standard safety properties. And that's how we did our real evaluation. We said, okay, let's ensure that there is no undefined behavior.
hmm,
And so that was our definition of bug for our evaluation. But in
right,
general, you can go through and you can write assert statements in the program.
hmm,
And and then the condition that you compute says that if you satisfy these constraints on the tables, those asserts will never be violated.
got it.
And so
Okay,
there is
yeah,
some amount of user, this is not entirely push button.
sure,
It can be push button for these standard safety properties, but if you want some bespoke property, maybe like a foreign key constraint, you would need to encode this in terms of assert statements, which is not hard. I've done this. It's like 2 assert statements, but then you can infer the corresponding foreign key constraint in logic.
right, nice. And in fact, this means that your tool is effectively, I don't know, parameterized in some sense over such safety properties, right? So you can
Yes,
actually
exactly,
use kind of whatever, okay, I guess for the moment, whatever safety properties you can encode as assert statements in P4, but perhaps
exactly.
theoretically, yeah, something else.
So presumably
Very
we
cool.
haven't done this, but
Right.
presumably you could even go back to this uh,
Right.
this picture here,
Mm.
right? So presumably you could even replace the safety check with this compatibility check in that algorithm and compute some uh, you could compute this lens contract. I haven't done this, but
Right.
in theory this is possible. Um, I think the challenge here would be making it scale and making it actually work, uh,
Right.
because it would probably presumably work for small P4 for small programs, but as soon as you get to anything large, you're now dealing with a massive exponential blowup that would need something smart to tame that we haven't invented yet. So, um,
Sure. Yeah, that makes sense. Okay, and so now, your original pitch, I guess, was about these routing abstractions that you have that get encoded down into potentially different P4 programs, realizing different switches, different switch pipelines, but ultimately resulting in, I'm expecting, based on this, the sort of the same behavior, right? That's kind of your
mhm,
compatibility
mhm.
compatibility criteria. And now
Yeah,
the safety properties are not really properties of multiple of these
right,
programs, right? The
exactly.
safety properties on a kind of on a per program basis, and it's only once
Yes.
you get to compatibility, I think that these are about program pairs really. Um, but I guess I see that I think now that your notion of compatibility, um, maybe I was trying to pull out the notion of compatibility from this. So it seems clear from your description, at least, and kind of formal definition, that it's essentially the routing abstraction in one that satisfies, safety property X satisfies safety property Y in this other program. I guess I should have called it phi and phi or whatever, but either way. Is there also? I guess there's also this packet condition. So this is the semantic part. Is that how I should think about this? That this is saying that actually they have the same semantics.
Yes.
And I guess I don't see the routing abstraction coming in here again. I would have expected that you might need to sort of say, restricted to this subset of the routing abstraction, or otherwise there would be, too many ways. Like even in this example program that you showed with the next hop and rewrite, I would have expected by kind of not having this always drop at the end rule, that I would have been able to produce something that you couldn't map back to the old program.
Yes.
Right.
Yes, that's right.
Okay, so
what's the deal? Yeah, so you're right on all accounts. The question the question of relating this back to the routing abstraction is basically that's what this lens is doing. So the point is, if you want to write, you can write this new driver by basically commuting the diagram in PL speak. So the idea is that the routing abstraction produces a driver to the old table, and then in order to get a driver for the new table, you just compose it with in the downwards direction, you compose it with the forwards part of the lens, and then in the upwards direction, say to handle route entry insertion failures or whatever else, you compose it in the reverse direction with the backwards function. So that's how you connect it to the routing abstraction. Now, if you're doing something like ONOS, where you have a formal specification of your routing abstraction, you don't need to go this route, right? You don't need to sort of do this evolution composition thing. You can directly relate your, instead of being old.p4, let's see if I can, instead of this being old.p4, this is your p4 model of the routing abstraction.
Sure. Right. Okay. That makes sense.
My goodness.
Very nice. And I guess I expect you have this, but in these examples that you had that you actually run this on, do you have any where you just get like no? And if so, is that kind of your tool times out, or is that
well, so right
or is
now
it reasonably efficient to see no, this is totally not doable actually?
Yeah, so the trick is right now this is all manual. So basically what happens is if it says no, it's because I failed to write a good proof. And there are situations where it fails to write a good proof or where I fail to write a good proof and it fails to check. Again, in PL parlance, we're doing a kind of like liquid style verification tool or something with Hoare logic. And so you can basically, if it fails to check an implication between intermediate invariants on intermediate states, then you know that it's bad, and you need to do some reframing or rewriting of these predicates. So, but in answer to the other part of your question, which is this fast? The answer is yes. I haven't encountered any timeouts, which is sort of unusual for these kinds of tools. But again, we're in manual verification mode, so it's unclear how that would generalize to sort of a push button verification or even a synthesis tool, where I would expect that you would reach timeouts, and you'd have to somehow provide hints or restructure something in order to guide the tool to the right answer.
Got it. Okay, and so maybe this is sort of what one should expect in terms of some kind of incompleteness relation that actually you cannot plausibly say this is it's very hard to get a result that truly says this program will actually never work versus you've chosen a bad contract.
Yes. In some sense, because we have finite domain, like Like
It's possible.
it is
Yeah.
decidable, but like
Yeah.
see you in a million years kind of thing.
Yeah. Yeah. Yeah.
So, but doing it in practice is the question.
Right.
Yeah.
Got it. Cool. Thank you very much, Eric,
Yeah.
for
Thanks
your
for having
time.
me.
This has been very exciting.